So we're going to talk about model-based classification. So model-based classification is also called hypothesis testing. So the framework for that is as follows. You have, the observation or a data point, X. It can come from one of K classes. So the classes we'll label as before as 1 through K, and somehow somebody has given you a model for the data given the class ID. So basically you might get this model through training somehow. We'll discuss that, how difficult that could be sometimes. You could get this model through physics, if it's a physical system, through engineering intuition. So there are many ways in which the model can arise. But suffice it to say, you are given all these so-called conditional distributions. So that's what the conditional distributions or densities of the data given the. So if somebody is nice enough to give you these models, then there's a very sensible decision rule that you can come up with. The maximum likelihood rule, and we'll abbreviate this by ML as well, even though ML we also reserve for machine learning depending on the context. So the maximum likelihood rule just says pick the max. Basically, pick the label that just maximizes the conditional density. So now remember that when the data is given to you, this P of X given K is no longer a function of X, because X is not varying. That's the data point that's given to you. It's now a function of the label or hypothesis K. And you have to maximize over that. And you pick the K that makes this the largest, and that's what we call argument of maximum. So where the maximum is happening, and that is your Y hat. This is the Y hat, the maximum likelihood Y hat, which is of course depends on the data point that you actually see. So let's just illustrate this by an example. Suppose you are given that, now let's just consider two hypotheses here, two classes. So then we'll call them 0 and 1 rather than 1 and 2, as we usually do when there are only two classes. Let's suppose that one of them is uniform from, say, -2 to +2. So uniform from -2 to +2. This is what the density looks like, and of course the density has to integrate to 1, so its height is 1/4. So the area under the curve is 1, and let's say this is P of X given 0, right? So as a function of X, this is my density. So that's P of X given 0, and let's pick the other one to be a Laplacian, which is just a symmetric version of an exponential. So we'll make it look like this. It's symmetric. This is P of X given 1, the function of X. And let's say that it decays as e to the minus the magnitude of X. And it's pretty easy to see, to make the area under the curve 1, this factor has to be half. And so the maximum likelihood rule just says, well, given a particular value of X, you have to make a decision as to which one it is, and you just do it by comparing these two densities. If the top density is bigger, then you will say 0. If the bottom density is bigger, you will say 1. So let's just see what it looks like by overlapping one on top of the other. So when we overlap one on top of the other, let's see, let's draw this. You have to, calculate the numbers, but let's see, this is -2 to 2. This height is 1/4. The other one is half e to the minus magnitude of X. So at 0, at X equals 0, the height is half. And we can check that it decays like this. So basically it will look kind of like this. So this is I should probably have done different colors. So this is P of x given 0. This is P of x given 1. And let me switch colors now to red. And now basically we can see, all right, out here you have P of x given 1 bigger than P of x given 0. So your y hat will be equal to 1. That's the maximum likelihood rule. Out here you have that the conditional density given 0 is bigger than the conditional density given 1, so you have y hat equals 0. Similarly here too, y hat equals 0. And of course beyond 2, basically p of x given 0 is 0, so all this stuff is y hat equals 1, y hat equals 1. So that's your maximum likelihood rule pictorially depicted. So now that we've seen what the ML rule or maximum likelihood rule looks like, let's look at the Bayesian approach. So Bayesian approach, that says that in addition to knowing these conditional densities, you also know, before you've seen any observation, any data point at all, you also know some prior probabilities. So that's the additional ingredient that comes in. So that's the probability of each hypothesis or label before you have seen any data points. You could learn this from data as well, but basically somehow somebody has given it to you. Either you have learned it, or you just say, I'm just going to assume they're all equal because I don't know any better, right? One way or the other, somebody gives you the prior. Now you can actually apply Bayes' rule to compute posterior probabilities. So now you can say, okay, now that I've seen my data, can I compute what's the probability that y is equal to a particular hypothesis given that I've seen the data? And so now I apply Bayes' rule and say, okay, this is going to be probability of x given k times the probability that, y equals k divided by the probability of x. Now look, if you think of x being a continuous random variable vector, we are mixing discrete random variables, that is the y takes one of k values, and potentially a continuous random variable or vector x, and that's perfectly legitimate. Bayes' rule can be applied in that fashion. This is you can go back to your basic probability to check that you can indeed do that. So anyway, you do this, and then this p of x at the bottom is a normalization constant. And so now that you've somehow computed these posterior probabilities, you can now say, okay, I'm just going to maximize over these posterior probabilities, and that's the so-called MAP rule, maximum a posteriori probability rule. So the MAP rule just is y hat map for any given data point is just arg max over k. So pick the hypothesis that is the most likely given the data you're seeing. So that's the MAP rule. So when we look at the posterior probability, we see that there is a part that depends on k, the variable we are maximizing over. That's this part. And there is this other part that does not depend on k at all. So when we are maximizing over k, we can drop the part that does not depend on k. And so the MAP rule can also be rewritten as arg, I'll keep with the red just to show that it's a different form that I'm writing. Argmax of basically p of x given y equals k times the probability y equals k. These are the two terms that depend on k. And often, of course, these conditional densities have an exponential form, so it's often convenient to write this as argument of the maximum of the log of these quantities. And so when I take the log, this product becomes a sum, and I have log of the conditional density plus log of y equals k. And we'll apply this this form when we take the example of Gaussian distributions a bit later on. But before doing that, I just want to go back to that example we had and show how the map rule differs from the maximum likelihood rule potentially, depending on the prior probabilities, right? So remember that we had these two densities. One of them was conditional densities. One of them was a uniform from -2 to 2. This was P of x given 0. And the other one was exponential. Laplacian. Basically a symmetric version of an exponential, which looked like so. This is my P of x given 1. And now, and the maximum likelihood rule, you can see basically is a special case of the map rule when all the hypotheses have equal prior probabilities, right? Because then the P of y equals k terms all just sort of go away because they don't depend on k anymore. So that's the maximum likelihood rule. But now suppose you have a higher probability of say probability of x given 0. So suppose you have a prior probability of y being equal to 0 of say 2/3, and probability of y equals 1, hence obviously is 1 minus 2/3, which is 1/3. So now we are basically, in this case, we'll just compare it based on the sort of the product thing, where P of x given k times P of y equals k is what we are comparing across these values of k. So basically, let me try to draw what that looks like. I'm basically going to multiply. I'll do it on just one figure. So basically, P of x given 0 times P of y given 0 is will be 1/4 times 2/3, which looks like 1/6. So I'll just draw something. It's not to scale. Let me call this 1/6. This height 1/6. And then this guy, half times 1/3 will again be 1/6. So I have chosen this really wisely. So this is also 1/6. And so let me just label these. Let me switch pen color here and label these. So this guy is actually P of x given 0 times P of y equals 0. And this guy is P of x given 1 times P of y equals 1. And it just so happens that we have chosen those prior probabilities such that over this, let me switch back the pen color, over the support of this of the P of x given 0 density, it's always bigger. It just happens to be always this product always is always bigger for P of x given 0 times P of y given 0 is bigger than P of x given 1 times P of y equals 1, right? So basically what we have is out here, we will say y hat map equals 0, and out here, because the P of x given 0 density has no support, we have that this product is bigger, and y hat map is 1 and y hat map is 1 here. So that's basically an illustration of how the map rule can be different from the ML rule when the priors are different from a uniform prior.